Another class of compounds that reacts with alkenes quite readily are so-called 1,3-dipolar compounds or 1,3-dipolar reagents. And a number of them are shown here. The important thing about these is that they are all compounds that are best represented by a group of resonance forms that indicate that there's delocalization of electrons across 2 or 3 atoms in the structure. Diazo compounds, shown here, represented by these 3 resonance forms. But then there are some really interesting other compounds. Nitrous oxide, this is probably the best resonance form you can draw for it. Nitrile oxides, interesting sort of class of derivatives of nitriles. Azids, nitrones, and probably the most abundant and the most interesting of the bunch is ozone, this allotropic form of the element oxygen that you're familiar with in different ways. And we're going to look at how ozone reacts with alkenes. In organic chemistry, ozone is most commonly used to do ozonolysis of alkenes. And this is an interesting reaction in that it's a cleavage reaction. It actually breaks the carbon-carbon bond up. And if you look at the overall process, you can see here, the alkene is treated with ozone, and then this is followed by some sort of reductive workup. And there are a variety of ways of doing this reductive workup, but you need some sort of reducing agent. The result is cleaving the carbon-carbon bond, and then the 2 carbons are oxidized to carbonyl oxidation state. So depending upon the structure of the alkene, how many alkyl groups or hydrogens are attached, you can end up with ketones, you can end up with aldehydes, you can end up with formaldehyde as one of the products. And below are a few examples of this simple ozonolysis procedure. Ozone, by the way, can be generated in the laboratory using a benchtop device known as an ozone generator. It's hooked up to a cylinder of oxygen. The oxygen is run through and essentially passed through an electric arc that causes reaction of oxygen to produce some concentration of ozone. And then that stream of ozone gas can be added to the reaction in some fashion. This is typically done at low temperature. I'll talk more about why the low temperature is necessary. And then once that reaction is complete, then typically right into the reaction vessel, you add some sort of reducing agent. You can use sulfides. This is dimethyl sulfide. The drawback with using dimethyl sulfide is this is the thing that makes rotten eggs smell like rotten eggs. But you can also use metals. Zinc is very commonly used in this, so mild reducing metals. So look at the overall reactions in each one of these. And you want to think about this as cleavage of the carbon-carbon double bond. So slice these double bonds up and think about what the 2 halves will be once they're broken apart. And you replace the carbon-carbon double bond with a carbon-oxygen double bond. So here we would end up with these 2 products. This is an aldehyde, that is formaldehyde. If the double bond is in a ring and you cleave it, you'll open the ring and then those remaining 2 carbons will be oxidized. And so here we end up with this 6-carbon chain with aldehydes at each end. In the last example, we have 2 methyl groups on one side, 2 hydrogens on the other. We end up with acetone and formaldehyde as our products. Now, hopefully you're being thinking is, well, wait a minute here, we're taking big molecules apart, making them into small molecules. And in fact, this is not terribly commonly used as a means of synthesizing things, but rather as a means of breaking things down into smaller bits so that you can determine their structures. So mechanistically, this happens in 2 parts. The first part of the reaction is the reaction with ozone. And it's a complex mechanism that I probably won't ask you to reproduce, but it's worth kind of thinking about what's happening. And one resonance form you can draw for ozone looks like this. And this one is useful for drawing this mechanism because we have a formal positive charge on one end and a formal negative charge on the other end of the ozone. So you can think of this as being both electrophilic at this end and nucleophilic at that end. So the pi bond will add to the positive charge, but the negative can add back to the other end of the carbon. And this happens in a concerted fashion and produces a five-membered ring with three oxygens in it. These are known as mol ozonides, and they are discrete intermediates in the reaction. They're also sometimes called primary ozonides. And they do an interesting thing. They immediately decompose and split apart into these two components, where we have an aldehyde and we have this dipolar species that we hear. And this is a 1,3 dipolar species, much like uh, seen on the first slide. This dipolar species can add back in a fashion to the double bond where it flips over from, and in this case we've shown um, the um, the aldehyde here flipping over to the other direction. This happens largely for steric reasons. These alkyl groups want to be as far away in the structure as possible. And so it adds back again. This is another 1,3 dipolar addition. And we produce what's known as the final ozonide. Both the mol ozonide and the ozonide are unstable species and can explosively decompose, which is why we keep the reaction at very low temperature during this process. So in those previous examples, you notice those minus 60, minus 78 degree temperatures. As long as we keep them cool, they're stable. But the ozonide here is stable at those temperatures, so how do we break it down carefully? And the answer is we add a reducing agent. And that reducing agent cleaves it into the final products. That mechanism is a little beyond the scope of the course. So again, let's look at some examples of ozonolysis and the products that we would produce from them. So here we can see if we split this, we would end up with these two products. This is cyclohexanone and acetone over here. And this last one is kind of a good example of why you would use this. It turns out that the structures of fatty acid esters, this is a fatty acid, long carbon chain. Somewhere in that carbon chain is a carbon-carbon double bond. How do you figure out, using analytical methods, where the double bond is along that carbon chain? IR won't tell you where the double bond lies in the chain. It'll just tell you that you have a double bond somewhere. NMR won't work because the signals would be overlapping in these regions. So the way that you figure out what the structure of this compound is you very cleanly do this ozonolysis. It splits this into two pieces, and then you analyze that final mixture and um, determine, you analyze that final mixture and look at the two structures that you form in that mixture, and then we can reason backwards to, oh, that's where that double bond was. It must have been between carbons 9 and 10 in this long carbon chain. Here are more examples of that. Again, you want to think about this kind of in the reverse form. What are we doing in these reactions? And the answer is we're connecting um, these carbonyls. So these carbonyls in the structure, we're connecting those carbons. So this carbon needs to be connected to that carbon by a double bond. Likewise, in the structure below, we're connecting these carbons that bear these carbonyls. So this carbon must have been connected to that one by a double bond. So if you look at the example above, very clearly this is the carbon-carbon double bond. So we have this chunk, which is the molecule down here, and then we have this portion of the molecule, which is this one that we see over here. And notice it's just drawn in a different way. There's two methyl groups attached to that carbon, two methyl groups attached to that carbon. In this one, since we have a single compound with two carbonyls in it, we would rationalize that this must have been a ring. So how big was the ring? All we have to do is count. 1, 2, 3, 4, 5. It was a 6-membered ring, double bond between this carbon and that, so that methyl group must have been a substituent on the ring. So those were all examples of ozonolysis with a reductive workup, and we ended up with these carbonyl compounds. You could do ozonolysis and add an oxidizing agent. This is typically done with acidic hydrogen peroxide. So it looks like a similar thing. It cleaves the molecule in half. And the only difference here is that the carbons that were part of the double bond, these two carbons here and here, those carbons, after we've cleaved the double bond, are oxidized further. So instead of being aldehydes, for instance, they're oxidized up to carboxylic acid oxidation state. And so we can see a few examples of that. Cleave this compound, we'd end up with formic acid and this long carboxylic acid. If you cleave cyclohexene, you'd end up with this dicarboxylic acid. This last one is instructive because you can see that we end up with formic acid here. The other half of this, because we had two alkyl groups attached to this carbon, can't be oxidized further. Generally, ketones stop and you can't oxidize them further to the carboxylic acid oxidation state because that would entail cleaving a carbon-carbon bond. Now let's kind of shift a little bit and talk about other electrophilic additions to alkenes. One is, and these are examples, are the use of permanganate and osmium tetroxide to react with alkenes and form 1,2-diols or glycols, vicinal diols. Both of these reactions work, but they both have their pluses and minuses. Potassium permanganates, the upside for potassium manganate is it's cheap and readily available. The downside is that potassium permanganate is a powerful oxidizing agent, and often this reaction can go too far. It can over-oxidize and end up cleaving this carbon-carbon bond. The second reaction sequence, the use of osmium tetroxide followed by sodium sulfite, has the advantage of being very mild and very specific, typically gives very high yields, but it turns out osmium is a rare metal and extremely expensive. So this is only used in very specific scenarios. So here's the first example where we use permanganate, a little basic water. This is all done in one pot, and if you're very careful, keep it at low temperature, you can isolate the vicinal diol. Notice the stereochemistry here. This is very different than what we've seen before. This is a syn 1,2-diol addition. Now, I just so happened in my past to have done many of these types of reactions with osmium. The conditions are slightly different, but basically the same here. Osmium tetroxide followed by sodium sulfite. And you can actually find the experimental procedure for this in my dissertation from way back when. In this case, I needed to make the diol out of this double bond at the end, and the rest of this molecule is very sensitive, so there's no way I could have used potassium permanganate. And so we went reasonably well, 88% yield, isolated yield is pretty good. So what are these things doing when they react to the alkane? And the answer is they're reacting to form some sort of metal complex, and they do so by a one-step addition. So this is similar to the 1,3-dipolar compounds. And mechanistically, it's the alkene kind of reacting with an oxygen metal oxygen group in these metal oxides. And you end up forming these esters. This is called a manganate ester. This is called an osmate ester. And the only difference here is the oxidation state of the metal is slightly different. So the manganate exists as a salt, whereas the osmate is a neutral compound. Because these add across the double bond and form an intermediate ring, the stereochemistry of that addition is retained. And so if you use osmium and it adds to this double bond that is shown here, it can either add to the top face and form that ring up here, or it can add to the bottom face and form the ring down there. Regardless, the two oxygens that ultimately end up as alcohols are added to the same face. And so you either produce the syn diol in this fashion and the syn diol, and you would get equal amounts of those. Previously, we'd looked at hydration of alkenes using mercury, so an oxymercuration, demercuration. You can also hydrate alkynes. It has a very different outcome, as it turns out, and it's a one-step reaction rather than two reaction sequence. In this case, what we use is we use mercuric acetate and acidic water. And under those conditions, reaction occurs to hydrate the triple bond, so we add hydrogen and hydroxyl. But this intermediate structure that's formed, known as an enol, ene for the double bond, ol for the alcohol, these are unstable structures under these aqueous conditions, and they rapidly undergo an isomerization. So this is an isomerization, so this is a structural isomer of that, and it's considerably more stable. And so it goes from an enol to a ketone. This is sometimes known as the enol ketone tautomerization. It's a very common transformation. So here are a couple real world examples. Here we have a triple bond at the end of a chain. So you can think of this as a triple bond that has a secondary carbon on one side and a primary carbon on the other. And if we look at the product, we can see that it is regioselective, that the oxygen adds to the more substituted carbon, and that's where we end up with our carbonyl. If the triple bond is in the chain, this is a secondary carbon, that's a secondary carbon, there's no selectivity, and we would get equal amounts. So the initial enol can form in either way. And it doesn't matter that one alkyl group is longer than the other alkyl group. So how does that enol form, and then how does the enol transform into the ketone form? The enol forms in a fashion similar to what we saw with the reaction of mercury salts with alkenes. We would form a mercurinium ion intermediate. It's a somewhat strained three-membered ring with a positive charge on mercury, and it forms in the fashion you're seeing here. Under the aqueous conditions, water is a good nucleophile. It will add to one of those two carbons. This opens up this three-membered carbon-carbon mercury ring to form this vinyl mercury derivative with an oxonium ion. The oxonium ion is deprotonated in the usual fashion. But then things don't stop. In the case of this, with this vinyl mercury compound, these undergo protonation, and they protonate such a way that they protonate the carbon that bears the mercury. And at that point, this can have a loss of mercury because the mercury +1 acetate ion is a relatively stable ion. So it essentially donates its electrons and floats off into solution, and we've reached the enol stage. All right, so then what happens to the enol? The enol undergoes what we commonly refer to as tautomerization. It's such a common type of isomerization, it has its own name. And here's how it occurs under these acidic conditions. The double bond is protonated. You've seen this happen before in hydration of alkenes. It's going to protonate to form the most stable carbocation. The carbocation adjacent to the oxygen will be stabilized by resonance. You recall how that works. But under these conditions, that carbocation can be deprotonated because it's a hydroxyl group, and that deprotonation leads to the keto form. And this first step is energetically uphill because it's producing carbocation, but the driving force for this is the formation of the keto form. Significantly more stable than the enol because of this strong carbon-oxygen double bond.